Thank you very much. First of all, I'd like to thank the organizers for giving me a chance to talk in this wonderful workshop. In this talk, I'd like to talk about our works on so-called Bion saddle points, which are expected to play an important role in understanding non-particle physics and resurgence structure in CPN signal model. So this talk is based on the series of papers in collaboration with these people. So one of our motivation to study resurgence is to understand how to evaluate the path integral in physical system like field theory. Quantities like a partition function is usually given in the form of path integral like this. And formally, it is said that this kind of path integral is a kind of integral over all field configurations. So, but of course, it is almost impossible to explicitly evaluate this kind of integral over all field configuration. So we have to use some approximation method. The one of approximation methods which we can use almost all cases is the perturbative expansion with respect to some coupling constant in the model. And such perturbative expansion gives good approximation if the coupling constant is small. But but it has been known that such perturbation series is a kind of factorially divergent asymptotic series, and in many cases such perturbation series is very non-summable. So we have a kind of imaginary ambiguity, which is corresponding to the singularity on the Borel plane. So we expect that we have to take into account non-perturbative saddle points, the contribution of non-perturbative saddle points, which usually takes this form. Here, S sigma is the action, the value of action at the saddle point sigma, and this power series is the kind of perturbation series around the saddle point sigma. And then we construct Torrance series by appropriately summing these saddle point configurations. So then we expect that this kind of Torrance series gives a correct physical quantity, and we expect that there is no ambiguity here. So what we would like to do is to check if this is really gives the correct physical quantity or not. So the first step to construct this kind of Torrance series is to find the saddle point or critical points of the action. In terminology of physics, these saddle points correspond to the solutions of the equation of motion of the action S. But as in the case of ordinary finite dimensional integral, when we construct Torrance series, we have to take into account not only real solution but also complex saddle point solutions. So we have to consider an analytic continuation of action by regarding the action as a function of the holomorphic variable phi by complexifying that model. And then we can find the saddle point by solving the Euler-Lagrange equation, which can be obtained by taking the variation of action with respect to this holomorphic variable. Then we can find saddle point configurations corresponding to, for example, perturbative vacuum and instantaneous configuration, and so on. Then next step we have to take is to determine how to sum this non-trivial saddle point contribution. So we have to determine which saddle points are and which integration contours are relevant in this Torrance series. So this can be done by using the Lefschetz-Timber method. So in this Lefschetz-Timber method, we first determine the thimble J sigma and dual thimble K sigma associated to each saddle point sigma. Then we can use this symbol J sigma to calculate the saddle point contribution to the partition function J sigma. And we can determine the coefficient in this trans-series by looking at the intersection number between this dual symbol and original integration contour. So this is the procedure of this Resurgence method. But in general, it's very difficult to perform this kind of procedure in infinite-dimensional configuration space. So this is a kind of challenging problem. In this, in our work, we kind of indirectly solve this kind of problem by using a kind of reduction from infinite-dimensional configuration space to finite-dimensional subspace of this infinite-dimensional configuration space. And then by applying the Resurgence method in the finite-dimensional subspace, we somehow calculate this kind of partition function and physical quantities. So this is one of the main points I'd like to talk in this talk. I'd like to tell you in this talk. Okay, so the model we are interested in is the CPN -1 sigma model, which is described by fields which can be interpreted as a map from 2D base space M to target CPN -1. And action of this model is given like this. In this talk, we identify this field as the inhomogeneous coordinate of CPN -1 target space. And this GAB is the Frobenius-Trilly metric of the target manifold, target CPN. So because of this SN isometry, this model has SN symmetry. And this G is a constant, a Bayer coupling constant, and so we consider expansion and non-particle effects with respect to this Bayer coupling constant or renormalized coupling constant, which will appear after renormalization procedure. Okay, so this is a basic model we are interested in. The reason why we are interested in this kind of CPN sigma model is that this kind of model can be interpreted as a kind of 2D analog of 4D gauge theory, which like QCD, which describes our world. So it has been known that 2D two-dimensional CPN minus sigma model can be interpreted as a kind of toy model of 4D gauge theory in the sense that they have many common properties like asymptotic freedom and instanton and large n and mass gap and so on. So we expect that this 2D CPN sigma model has a similar resurgence structure as the 4D gauge theories. So we expect that we can accept that we can obtain some hint for so-called IR renormalization problem from relatively simpler 2D models. So our motivation is to use nonlinear 2D CPN sigma model to get a hint for this IR renormalization problem. So let me explain what IR renormalization problem is. So IR renormalization problem, okay. So in generic physical theory, physical models, it is said that factorial growth of the perturbation theories is related to the factorial growth of the number of Feynman diagrams contributing to the nth order in the perturbation theory. But in the theories like 4D gauge theories, it has been known that there is another source of factorial growth of the perturbation series. For example, this kind of diagram, which has n fermion loops in the larger loop, gives a kind of factorially large contribution, like the n factorial. So so this gives the factorial growth of the perturbation series. And if we take the whatever resummation of this kind of diagrams, then we get singularity in the Borel plane at 1 over g square n. So, so there must be some non-trivial saddle point corresponding to this singularity, but this cannot be the Yang-Mills instanton because the value of action for this Yang-Mills instanton is like 1 over g squared. So this is much larger than the value of the the position of this singularity. So and particularly this action of this instanton vanishes in the 2/5 limit, in the large n limit, and on the other hand, this singularity does not go away in the large n limit. So this Yang-Mills instanton can never be the singularity saddle point corresponding to this singularity.
Yeah. During the certain your CPN model, you don't go, you can say fixed and not go to large n limit, yeah?
No. Yeah,
it will not conform field suit, depends on metric on the surface.
Yeah, right. Yes. Yeah. So, okay, anyway, so from this argument, we expect that there is other saddle points that is called renormalon. And this has been a long-standing problem because we could not the saddle point corresponding to this renormalon has never been found for a long time. So this is the IR renormalon problem. But several years ago, there was Algiers and Unstall gave a proposal for this candidate for this IR renormalon that is called Bion. This Bion is a field configuration which consists of a pair of fractional instanton and anti-fractional instanton. So these two objects are play an important role in this talk. So let me explain what.
Zero topological church, isn't it?
Okay. Yes. Right. They don't have the. Okay. Bion doesn't have topological church. Okay. Let me explain what they are. So. Before that, let us look at some figure just for fun. Okay, this is a figure of an instanton on cylinder, instanton in CP1 sigma model on cylinder. So here, this red region corresponds to the location of instanton, and if the size of instanton is much smaller than the radius of this compact direction x, this instanton looks like an ordinary one single instanton. But if we shrink the size of S1, then this instanton splits into two objects. And this is in the case of CP1 sigma model. If we consider CPN minus 1 sigma model, single instanton splits into n fractional instanton. So okay, each of them are identified with a fractional instanton. So okay. So this plays an important role. So let me explain this object more in detail. So okay, so the model we consider is the CPN minus 1 sigma model on cylinder. And in this talk, I will always call the non-compact direction as Euclidean time, and I will denote it by symbol tau. And spatial direction is denoted by x, and it is compactified with period 2 pi r. Then action we consider it like this. So this is actually a little bit different from the previous one because the derivative is now replaced with the covariant derivative. So this means that there is we introduced the background gauge field for SUN global symmetry, MA, which takes value in the Cartan subalgebra of SN global symmetry of this model. So we introduce this kind of background gauge field. Basically these parameters can be arbitrary, but if we consider this specific value of the background gauge field, and this action has an enhanced Gn discrete symmetry. So this value of background gauge field is called a Gn symmetric background. And the important point is that if we choose this background, then it is expected that this model has so-called adiabatic continuity. By using this, we can continuously connect the weak coupling description of this model to the strong coupling description on R2. So anyway, we are mainly interested in this Gn symmetric case. Okay, anyways, let us solve the equation of motion of this model to find the saddle point of action. We can easily find the solution of the equation of motion by rewriting the action into the sum of positive semi-definite term and topological charges. In this model, there are two relevant topological charges. One is ordinary instanton number, which is given by the integral of the Kähler form, product of the Kähler form. And another topological charge K is given by this quantity. So this is so sigma is a kind of obtained by the fairing of the moment map of SN and the background gauge field. But anyway, this quantity gives a difference of values of this sigma in the future infinity and the infinite past. So this means that this quantity depends only on the boundary conditions. In this sense, this is topological. So these two topological charges are invariant under continuous deformation of the field phi. So we can easily get the solution of the equation of motion by minimizing the positive semi-definite part, which takes this form. So this is positive semi-definite, so we can easily minimize this quantity just by requiring that this equality holds. Then we get these BPS equations.
I'm sorry, this M are just constants.
So yeah, right, yes.
So you just deform the standard CPN model and consider a zero set of M, right?
Right.
Okay.
Just the question, because it's zero, it should be, there are contra terms, yeah, because there is a normalization.
Yeah.
What is the contra term on this?
Actually, at this moment, we don't consider, we just consider only bare action. We'll introduce the counter term later.
Should we interpret this correction to action by something, yeah?
Yes. Yes. Okay, so yeah, now we are considering only bare action. Okay. So this is a BPS equation. This can be easily solved by this is just a very simple equation. So we can get the general solution like this. Here, FA are arbitrary Laurent polynomial of the coordinate on the cylinder defined in this way. Okay, so this is a general solution. So we, by choosing various FA, then we can get various BPS solution of equation of motion. The most basic solution is the single instanton solution, which can be obtained by setting one of FA to be degree 1 polynomial and others to be 0. Then this configuration is a kind of single instanton solution because the instanton number is 1. And then we can calculate the action, the value of action for this configuration. Then it's given by 2 pi over g squared. But this value is much larger than the value of action expected to be accepted saddle point for the IR renormal. So this.
What is the definition of instanton number? Is all the characteristics of the bundle, vector bundle over R cross S1, but it's trivial bundle, so it's 0.
No, but it's kind of normalized because it's not kind of not complex space. It's integral of curvature. Yeah.
Okay, so yeah, so instanton cannot be the IR renormal. So so what we have to find another solution that can be responsible for this IR renormal. That is a fractional instanton, which can be obtained by setting one of FA to be constant and others to be 0. So this is the solution of a fractional instanton, and this solution has 2 degrees of freedom corresponding to position moduli parameter and internal phase moduli parameter phi. Anyway, if we plot the function sigma as a function of tau, then we can see this kind of kink profile. So basically this solution, fractional instanton solution, is a kink solution corresponding to a kind of tunneling process between different minimum of action. So, and we can calculate the value of the action for this kink solution, then we get this value. And if you set the value of this background gauge field to the Gn symmetric point, then we get this value of action, 2 pi over g square n. So this is 1 over n times single instanton solution action. So this can be, this is...
Sorry, this is a sort of on-shell evaluation, right?
Sorry?
This is sort of on-shell evaluation.
On-shell evaluation, yeah.
Okay, so that you get solution plugging back to the
Right.
corresponding-
Yes,
okay,
yeah,
okay.
yeah, yeah. So this is 1 over n times single instanton. So, and this is the same order of the expected value of the action for the IR renormalum. So this can be a IR renormalum. But actually, the fractional instanton does not contribute to the partition function, because partition function partition function receives contribution only from periodic configuration along this Euclidean time direction, the compactified with period beta. So fractional instanton is a kind of kink tunneling process, so this cannot be periodic. But if we consider Bion configuration, which consists of kink and anti-kink, then this kind of configuration can be periodic. So this kind of Bion can have a non-trivial contribution to partition function. So the question is if Bion, this kind of configuration, can be identified with the renormalum or not. This is a question we want to consider. Okay, so yeah, in our work we explicitly calculated this Bion contribution by using the Lifted-Temper method. So I would like to talk about this explicit evaluation of this Bion contribution.
Sorry, can I ask a question? How do we know that it exists in the m equals 0 limit?
In the m equals 0 limit, this solution doesn't exist. But so the point is that so this is theory on defined on the cylinder with this periodic boundary condition, and we expect that if we choose this value, then there is a adiabatic continuity. Then if we take the R infinity limit, this vanishes, but because of discontinuity, the theory on R2 without this M is related to this theory.
How does one prove this assumption or justify it?
Yeah, actually, yeah, in the large n limit, there is a proof that there is no, actually, in the large n limit, there's a kind of, how to say, volume independence. So we can show, but for general n, it's a kind of conjecture, I think.
So it means like in a large n limit, I will never obtain Bion solutions, also now stable, or
In a, sorry?
in large n limit you don't have Bion solutions?
No, no, actually, I think we expect that there are Bion solutions also in the large n limit.
But then these will be different Bions, no?
Different?
Yeah.
Why do you think so?
I mean, because it will correspond equivalent to this formula, because this deformation of parameter from your equation is gone.
Actually, okay, oh yeah, simple, yeah, if we take the simple large n limit, yeah, this will disappear, but if we fix this n R, then we can get some configuration.
Okay, so this is intercombination n.
Yeah, yes.
But, sorry, it's you written that Euclidean time is just infinite, so it's well, there is no temperature, right?
Okay.
And then you introduced the temperature and written the solution, which depends on your tau but not on x, right?
Right.
Sample loss.
Okay, yeah, at this moment, I just considered zero temperature limit, but when we calculated partition function, we introduced the temperature. So we consider...
The solutions which you reach, and they don't depend on x, right?
Don't depend on this solution. Okay.
The solution, right, there was only tau dependence, but not x dependence.
Not next.
And they still satisfy the equations of motion, right?
This is
Okay, so I got it.
yes. So okay. So let me explain our model. So the model I want to consider is the it's better to use the 2D n equals 2 to supersymmetric CPN minus 1 sigma model. because actually this supersymmetry is not necessary to calculate this Bion contribution, but it's very convenient to consider supersymmetric model because we can check we can use the exact result to check our Bion solution is really correct or not. So this is a model. We added some fermionic terms, and okay, as I said, to calculate the partition function, we need to compactify the tau direction. So okay, we introduce a compactified period of this compactified time direction beta, and X is also compactified. So we consider theory on torus, and as I said, we consider the background gauge field along this compactified space direction, and we introduce the same background gauge field for bosons and fermions because in this way we can keep the supersymmetry in this model.
So from now you will be having toric partition functions, right?
Actually, okay, yeah. We want to consider kind of a generating function of this observable by adding a source term to this Lagrangian. So we want to consider this observable by evaluating the path integral for this action, and we consider endpoint correlation function of this operator by differentiating the generating function.
What is M there?
Sorry, M. Mu is the moment map of SN. M is the background gauge field. This is, takes value in the SEN the algebra, the algebra of SEN. So we consider this point correlation function. Actually, we can calculate in our paper. We calculated Bion contribution in general CPN model, but for simplicity, let us focus on the case of CP1 sigma model. Then the explicit form of action looks like this, and we consider generating function for this height of this CP1, and we consider the kind of correlation function of this operator. So the reason why we consider this kind of correlation function is that by taking the small radius limit of the space direction, then we get the quantum mechanics in the 1D limit. In this 1D limit, we can exactly calculate this correlation function by solving by using the Schrödinger equation. So the 0 point function is just a ground state energy, and it's of course 0 because of supersymmetry. And 1 point function is given like this. So this contains infinitely many non-perturbative terms. So this is completely fully non-perturbative. And more interesting quantity is the 2 point function, which takes this form. And actually this has a non-trivial resurgence structure. So let us closely look at this quantity. So by expanding with respect to the coupling constant G, we get this perturbation series for this 2 point function. So coefficient of this series is gamma n plus 1. So this is factorially divergent. But if we look at the non-perturbative part, we have here there's a so imaginary part of this non-perturbative contribution jumps at when coupling constant pass through the real axis. So, so this quantity has this kind of non-trivial resurgence structure. So another question we want to check is that if this kind of structure can be reproduced from the analysis of Bion. So that's another problem we want to discuss. Okay, so the first let us.
What is E2? How do you compute it?
Okay, E2 is the kind of this kind of 2 point function integrated over this Euclidean time, and we can use so in the 1D limit this model reduces to supersymmetric quantum mechanics, and we can solve the Schrödinger equation in the supersymmetric quantum mechanics. By using the solution of the Schrödinger equation, we can calculate this two-point function. Exactly.
So this is something on a strict limit of zero radius or something.
The radius limit, yes. So we can get this kind of non-trivial resurgence structure, and we want to check if this non-trivial structure can be reproduced from the Bion analysis. Okay, so let's first determine the Bion solution by solving the equation of motion. So we consider the complexification of target space by complexifying the target space. Then we use the coordinates of this space, phi and phi tilde, which so this okay, the original CP1 target space corresponds to phi tilde equal to the complex conjugate of phi. And then we consider the analytic continuation of action by regarding the action as a holomorphic function of phi and phi tilde. And then we solve this equation of motion for this by taking the variation with respect to phi and phi tilde. Because now we are considering the two-dimensional field theory, so the equation of motions are two partial differential equations, so it's very difficult to solve in general. So we consider this x-independent ansatz like this. Yeah, because so this x-dependent, if we use this x-dependent ansatz, we cannot consider saddle points which contains ordinary instanton, because instanton depends on x direction. But we are, if we are interested in the leading order non-tripartite contribution, which is expected to be given by Bion, then we can ignore x direction because the Bion configurations are independent of x. So we use this x-independent ansatz. Then we the equations of motion reduce to two ordinary differential equation. And actually, this model has two symmetries. One is time shift symmetry and phase rotation symmetry. So we have two conserved charges in this model. And the degrees of freedom of this model is 2. So we can use the two conservation law to determine, to completely fix the form of the solution in this way. So the solution is essentially given by the Jacobi elliptic function. And there are several parameters, a, omega, k. They are just complex constants depending on the parameter in the model, and a pair of integer pq. So pq is our integers labeling the solutions, which takes in this range. So this means that this solution, so there we have infinitely many saddle point solutions. And the important point is that these are complex saddle points, because for generic P and Q, phi tilde is not equal to phi bar because these are complex constants. So they are complex saddle points. Okay, so let us look at simplest example of a solution. So this is the real Bion solution corresponding to P1. This is a single Bion solution, which looks like this takes the form of sine hyperbolic in a beta infinity limit. So this is the orbit in the target CP1. So this corresponds to the tunneling from north pole to south pole to north pole. And if we plot this height function as a function of tau, then we can see that there are kink and anti-kink. So this is a Bion configuration. So this is called the real Bion solution because in this case, phi tilde is equal to the complex conjugate of phi. So this is a solution in the original CP1. But if we consider only this kind of solution, we can show that Suji ground state energy becomes non-zero because of this non-parallel contribution.
So Witten index is 0 in this case.
So
what is Witten index? If
sorry, this is
0, then Witten index must be 0, right? Is it?
Yeah. Okay. So this is okay. Witten index is n.
What?
N.
But then energy cannot be
zero.
Cannot be different from 0. If Witten index is non-zero,
yeah,
then the energy of the vacuum is 0.
Vacuum is
there are
0.
several effects.
Yeah. Yeah. Vacuum is so. Yeah. So this contradicts with the Suji ground state. So there must be another contribution to cancel this contribution. So that is a complex Bion contribution. This is also a p equal 1 solution with p equal to 1, which looks like a cosine hyperbolic in the beta infinity limit. So this is called a complex Bion because in this case phi tilde is not equal to phi bar. So if we plot the height function as a function of tau, then we can see that this is also like a tunneling solutions, but in the tunneling process, this value of height becomes complex. So this is very peculiar solution, but we need this solution to guarantee that the Suji ground state energy is 0. So, so this kind of a complex solution is important to obtain the result consistent with Suji. Okay, so this is the thing. These are the single Bion solutions, and for general P and Q, for example, this is a figure for P Q equal 3, 1. So there are multi-Bion in the configuration. So essentially, integer P is number of Bions, and Q is a kind of label of saddle points in P Bion sector, which basically controls the combination of complex and real Bions in the configuration. So okay, so this is Bion solutions. So now we have saddle point solutions. Now let us consider the semi-classical Bion contribution by calculating the leading order term in the Bion contribution. This part. So naively, we can calculate this kind of quantity by just by evaluating the determinant of this infinite dimensional version of the matrix of the second derivative. But actually, we cannot do this because in the weak coupling limit we are interested in, there are some nearly flat direction of action. So more precisely, we can show that this matrix in the weak coupling limit has some 0 eigenvalues. So this means that in the weak coupling limit, there are quasi-zero mode for which we cannot perform the Gaussian integration. So we have to be carefully treat the integration along this direction. So to do let us define a so-called body of action. Roughly speaking, this body of action is a kind of finite dimensional subspace on which the real part of the action is nearly flat. To define this precisely, let us define this set of configuration called Valley solution by it is parameterized by a quasi-moduli parameter corresponding to the direction of this zero eigenvalue of this operator. Then we can, by this Valley solution can be obtained by solving this Valley equation, which is obtained by projecting the equation of motion onto the normal direction to this direction. Anyway, so we can define this kind of set of configuration. Okay, so let me briefly, before showing the solution of Valley equation, let me briefly mention about the relation between Valley and the symbols. So symbols are defined by solving these flow equations, and in the Valley, this finite dimensional subspace, the flow equation is given like this. Here, S effective is the effective action on the Valley, and this GAB is the induced metric on this finite dimensional space. And we can show that if we have the solution in this Valley, solution of the flow equation in this Valley, we can embed that solution into the solution of this flow equation of original space. So this means that symbols in Valley is contained in the symbols in the original configuration space. So this fact can be used. This is very useful when we consider intersection numbers and so on. Okay, anyway. Okay, so yeah, we can actually explicitly write down the solution of Valley solution in the case of single Bion and weak coupling limit and beta infinity limit. So this is the solution. This is actually a kind of kink, anti-kink configuration because yeah, this is sum of kink and kink. And this value solution is parameterized by one quasi-modular parameter eta, whose real part corresponds to the relative position of kinks, and imaginary part corresponds to the relative phase degrees of freedom. Okay, this is a solution. And then actually this set of solution contains, of course, real Bion saddle point and complex Bion saddle point corresponding to these specific values of the quasi-modular parameter. Okay, by using this value solution, we can decompose the degrees of freedom into the direction along the valley and normal direction in this way. Then we can reduce the action in the weak coupling limit in this way. So here, this is the effective action, Bion effective action, which is defined in this way. And this is basically the function on the valley, action of the valley, the value of action on the valley, and saddle points of this function correspond to the Bion solution, real Bion and complex Bion solution. And for normal direction and the fermionic direction, we get the Gaussian form. So by evaluating integrating out the normal direction and the fermionic direction, we basically get schematically we can write the single Bion contribution in this way. So here, this is the one loop determinant corresponding to the functional determinant, which can be obtained by integrating out the normal direction and fermion direction. And we can evaluate this one loop determinant by using the Kaluza-Klein mode expansion, which is basically the Fourier expansion. And then for each Kaluza-Klein mode, we get this operator, differential operator, delta p and delta f becomes a kind of 1D shredding operator. So we can use kind of a technique to calculate the 1D, calculate the functional determinant for this kind of 1D shredding operator. For example,
Are you still considering 2,2 supersymmetric model?
Sorry.
Are you still considering 2,2
Yes,
supersymmetric
yes.
model?
Yes. Yeah, but background is non-BPS, so yeah, there's no such structure.
But since you have fermions.
Yeah, right.
Okay.
So by using this kind of technique to calculate the 1D shredding, functional determinant of the 1D determinant, then we get this expression for the one loop determinant. This is basically given by the sum over Kaluza-Klein mode, and this x is given like this. So this summation over the Kaluza-Klein mode is divergent. So this is actually this is a kind of ordinary UV divergence in field theory. So we can use some regularization in standard regularization to regularize this divergent sum. Then we get this expression for the one loop determinant. Here, lambda 0 is a cutoff scale introduced to regularize this quantity. Then by using this one loop determinant, we can combine this with the bare effective action to get the renormalized effective action, which takes this one. This renormalized effective action takes depends on the renormalized parameter epsilon tilde. This is shifted by the quantum quantum effect, and constant y, which depends on the renormalized coupling constant, which is defined in this way. So we get renormalized effective action.
R is here in this
Sorry.
previous equation.
Radius.
R,
Compactification is
compactification radius, yes. Then finally we get this form, which is expression for the single Bion contribution. So this is a finite dimensional integration over this quasi-modular parameters. So, but we are now considering the complexified theory. So quasi-modular parameters are also complexified. So we have to determine which saddle and which contours are relevant for this quantity. So that can be done by using the Resurgence number method. And actually for this renormalized action, we can explicitly solve the flow equation to determine the thimble and dual thimble. So this is a picture of the dual thimble. Actually, this is a 3D projection from 4-dimensional space. But anyway, we can explicitly determine the symbol and dual symbol. Then we can find intersection number and the integration path explicitly. Then we can evaluate the quasi-modular integral. Then we get this result for the generating function. Single Bion contribution to the generating function. So this is very complicated, but the important point is that this contains jump at the this imaginary g equal to 0. So this is so yeah, if the resurgence works in this model, then this should be related to the Borel singularity at the value of this exponential. So furthermore, we can see from this jump of this non-perturbative part, we can how to say. So this implies that the perturbative part of this quantity should have this large order behavior. Perturbative part should have this large order behavior. So this is kind of the how to say prediction from the Bion analysis, but it's very difficult to check this because higher order, large order behavior is very difficult to calculate in the field theory. But if we take the 1D limit, we can use the Schrödinger equation, and we can calculate this kind of higher order behavior by using the perturbative analysis, by using the tools like Bendau package, mathematical package. And then we can compare the Bendau analysis and Bion analysis by taking the ratio of these coefficient, then taking the Lagen looking at the Lagen behavior, we can see that this ratio approaches 1 for any value of the source parameter epsilon. So this means that Bion analysis resurgent. So Bion result is completely consistent with the resurgence analysis, resurgence argument. Okay. So, so this is a result in the CP1 model. We can easily generalize the result to the CPN-1 sigma model. And the important difference is that there are n-1 types of Bion, but for each Bion, we can repeat the same type of calculation. Then we can calculate the single Bion contributions. And so this is a result for the single Bion contribution. This is a jump of the single Bion contribution. So this is so there is a jump in the imaginary part of the generating function, but this is a little bit so difficult, complicated. So let us focus on the point, the GN symmetric point, by setting MA to this value. Then we get this expression for the generating function. So important point is that this is proportional to this quantity. So this is means that there is and we have a jump in the imaginary part of this generating function. So this means that for the perturbation series should have Borel singularity corresponding to this value of action, this point, 4 pi over GR squared n. So this is nothing but the expected value of the action for the IR normal. So this means that this result is completely consistent with the proposal that Bion is responsible for IR normal. Okay, so this is okay. So yeah, another thing I want to mention is that because in the 1D limit, our Bion solution is actually the general solution because there is no experience. So you can try to sum all order multi-Bion contribution, and p-Bion contribution can be calculated in this way. So this is very complicated, but also in this case there is a jump here, and by summing over the Bion number, we can get the Tranz series for this. This is the result. We can see that the ground state energy is 0, and this is completely consistent with the exact result. And we get this expression for the 2-point function. And here we have a jump in the imaginary part of the 2-point function. Actually, this is completely consistent with the resurgence structure, which can be obtained from the exact result. So this means that our Bion calculation is completely consistent in at all order in the Bion number. Okay, so let me summarize the talk. We explicitly calculated Bion contribution in CPN-1 sigma model, and we got completely consistent result with expected resurgence structure, and we got consistent result with the proposal that Bion is related to IR renormalon. And but to show that if this Bion is really identified with the IR renormalon, we have to check that if the higher order behavior of the perturbation series is really agree with our Bion result. So we have to check. We want to check explicit higher order perturbation series in CPN sigma model. This is an important future work. Okay, so I'll stop here. Thank you very much.
Thank you very much. So, any questions?
Well, I actually have two questions. So one is, did you try 0,2 and 0,1 supersymmetric sigma models, which kind of interpolate between these two extremes where you have all control and no control? And second question is, in 4 dimensions, we expect that confinement is governed by QCD strings. So in what sense this is analog of QCD string solution?
String solution. Okay.
The right mechanism for confinement in this 2-dimensional model.
Yeah, actually, that's the okay. For the first question, we tried n equals 1, 0, but in that case, yeah, actually we couldn't calculate the. So what was wrong? In a quantum mechanics limit, we can calculate anything, and the result is actually almost the same. But in the case of field theory, because renormalization is much more complicated. So yeah, we cannot do this kind of thing. So yeah, we cannot, we couldn't calculate that, anything in the case of field 2-dimensional n goes to 1, 0. And so for the second question, okay, so it's about confinement. Yes, actually, yeah, I have to say that 2D CPN sigma model is very similar to gauge theory, but not exactly the same. There are several differences. For example, 2D, there's no, for example, symmetry breaking phase transition in the 2D model, but in 4D theory, there can be such phase transition. So yeah, they are similar, but there are differences. So I think, yeah, we cannot use this completely, yeah. This cannot be the complete analog of the 4D theory.
Yeah, I appreciate it. Yeah, this renormals are kind of infrared renormals, yeah?
Infrared,
yes, but the renormalizations will provide that correction, yeah.
Okay.
Yeah, and in general, it kind of got confusing when you do, maybe not with this model, just rescale scattering constants is still kind of positive, yeah, in the sense.
Right.
But in a more complicated situation, you get several running scattering constants, means that actual it's some of very big numbers multiplied by actual things. It's how one can justify this Timble's picture, because you have solved equations more with kind of running coupling constants as well, yeah. In your situation, it's kind of you just rescale coupling constant, nothing else, so it will be the same equation of motion.
Right.
Yeah, but in a more complicated situation.
Yes. Okay. So yeah, that's. I think that's the point. So yeah, because we are now considering weak coupling regime, which means that coupling constant is small. But to access strong coupling regime, we have to use something like this kind of adiabatic continuity. So we cannot perform this kind of analysis for strong coupling regime, but we can use some this kind of property by using to access that regime.
Any other questions? Maybe I have just a small question, which is, you talked about the Fubini-Shruti metric on CPN minus one, but did you ever use the singularities? That has some poles because there's a denominator. Do you use the singularities of that somewhere?
Singularity.
A Fubini-Shruti metric.
Yes.
No, you in the complexification have singularities here.
Yeah, but do those appear in the calculations?
So I don't know.
The singularities of the Fubini-Shruti metric
Singularity.
on complexified CP.
Complex file. Okay. Yeah. Actually, yes.
It's a chart singularity, it's not a physical singularity, right?
Yeah. Actually, this complex.
Kind of singularity, but it's singular in the complex.
Yeah. Right.
In the complex.
In a complex case. Yeah. Actually, this complex Bion solution hit that singularity if coupling constant is real. But if we introduce complex by the coupling constant, we can avoid that point. So this is, actually that is an important point.
Further questions? Okay, so thank you, speaker again.